Let's move on to pretext-invariant representations. Before contrastive learning or deep cluster, there were these set of methods that would say, I'm going to take an image, reshuffle it, and then the task of the network is to take the reshuffled version of my data, my image, and then perhaps solve a corresponding jigsaw puzzle. So you would do some transformation, like reshuffling, and then you would predict some properties of that transformation, like the order. This patch is perhaps the first one. This other patch is the second one. You get the idea. Or this patch is the last one. You predict some properties, perhaps the indices of every single patch. Another type of methodology was perhaps mask some portion of your image and then predict the portion that was masked. Or perhaps rotate this image and predict the rotation angle. How much did you rotate it? Don't worry about pretext-invariant representation learning yet. I'm going to come back to this figure. But let's see what is the problem with this paradigm of taking a transformed image and then predicting the transformation or some properties of the transformation. You have a set of images. Each one of them is a tensor. It has a height, it has a width, it has C channels, red, green, blue. You're going to have a set of image transformation, like reshuffle your image patches, rotate your image, etc., mask it. You have a CNN, which is this convolutional neural network, which is going to give you some representations, which you are going to use to transfer them to a downstream task. And whenever you have an image, if you apply a transformation on it, it's going to end up with a superscript in terms of notation. What would you do? You would take this representation of your image, and this is perhaps IT, so there should be a transformation on it. And then you need to predict some properties of that transformation. Perhaps the order that if you apply on that image is going to give you the correct image. It's going to solve the jigsaw puzzle. But what is the problem? Many of these types of pretext tasks, like solving the jigsaw puzzle or correcting the rotation in your image, they're going to give you representations. So these representations here, or the V's here, that are going to covary with that particular transformation. So they are going to be highly correlated with those transformations, which is not a nice property to have. You want to have representations that are actually invariant to how you rotate in an image. This is actually one of the data augmentations that we do. If you take an image, rotate it, it is still the same image. If you take an image, reshuffle it, it is still the same image. So you're looking for representations that are invariant with respect to those transformations, not covariant. This type of training is going to give you covariant representations, which are not going to end up being good representations in the end. They are not going to be transferable. And as I mentioned, this Z here is a function that is measuring some properties of your transformation, like the angle of the rotation. So you are looking for representations that are actually invariant to those image transformations. That's why you're going to write down a contrastive type of loss. This is actually not going to end up being contrastive. It is very similar, but it's also different. If you have a measure that is going to give you how similar two representations are, the images that go under some sort of transformation, which is not going to change the underlying object, they need to be more similar than the negative cases that are totally different images. Perhaps the image of a car here or the image of a cat is different from the image of a tree, but the image of a tree reshuffled, it is still the image of a tree, or the image of a tree rotated, translated, cropped is still tree. So you take an image, push it through your convolutional neural network, it's going to give you one representation, that is VI. You take the transformed image, push it through your convolution, it's going to give you another representation. And these two representations, you want to encourage them to be similar. So what is your loss function? You have positive pairs, which are the same images. One of them is a transformation of the other. And at the same time, you are going to have a number of negative pairs, which are different images altogether. perhaps the image of a cat, dog, etc. You are going to model the probability that these two pairs of images are originating from your data distribution, are actually data, versus some image of a tree and the image of a cat, which are negative pairs. That probability, you are going to model it with some score and a constant here. If you are looking at your entire data set, this wasn't a mini batch, or your mini batch was the entire batch of data, then this would just be a 1, and you are getting your sigmoid function back. So this is different from softmax. This is a sigmoid function, and you're modeling the probability that I and IT are coming from your data distribution. Anything else, like I and any other image, I prime, are just noise. And you want to contrast the true data versus noise. And I'm going to tell you why you need to adjust for the size of the negatives, to adjust for the size of your mini-batch. This S is your cosine similarity. You're going to have noise contrastive estimator. If you remember, this is the second time that we're seeing noise contrastive type of loss. The last time that we saw it was when we were doing natural language, and we were doing word to vec, to take our word, to give us the representations for our words. Over there, any, perhaps you would take a context word, and then any other word in the same sentence was going to give you a positive pair, and any other word not in that sentence was a negative example. Here you want to increase the probability of positive cases and decrease the probability of negative cases. You have a lot of negative cases, so dn 1 minus h is going to give you the probability of these pair not originating from the data. You want to increase that, you want to increase this, you're trying to do the correct thing all the time. And where is this going to come in? If you write down 1 minus h, the fraction of dn over d is going to go in the numerator, and the other stuff, the denominator, is going to end up being the same. Now you're summing over the n of them, and this way you are weighing them proportional to each other. All of the negative cases are weighed similar to each other. So that's why you need to adjust this. You cannot use the sigmoid function. You need to adjust your sigmoid function a little bit. And this is the noise contrastive estimator. What are you contrasting? You take your features, push them through a neural network, and then compare the features from your image, the features from the transformed image. You compare the two. You take your transformed image and any other image in your data, and these are not coming from the same data distribution. This is noise, that is data. But you're not done yet. You have your image, you have the transformed image, push them through some residual neural network, get your features. This is f of v, this is g of v. You would like f of v to be similar to g of v, but if you remember the ideas from momentum contrastive learning, it's a good idea to keep a memory bank or a queue and compare yourself with a queue for computational reasons. You don't need to do these operations all the time. Just cache them and compare to the result. This should be similar to the correct answer, and this similar to any other answer, any other image, which is also cached. So wherever you have mi prime, mi, and mi prime, these are cached versions of your image representations. And f and g are just two different heads on top of the residual network. And as I mentioned, m's are just exponential moving averages of your features. These are cached versions of your features. It's going to give you something that is consistent, and you're comparing yourself to consistent stuff. What is your final loss function? You can take m wherever you see mi, think of f of vi, and then you are contrasting that with g of vit. So that's this loss function. You're writing it here, and g of vit the same, and this is going to end up being m of I prime. So wherever you have f, you're going to replace it with an m. Wherever you have g, you're just fine. It means that you are now going the opposite route. You're comparing the outcome of g to f, or a cached version of f, and some other dissimilar objects. And then this other one, wherever you have a G, you're going to use your M. And whenever you have an F, you're keeping F. That's how you're going to write down your loss function. And it's a symmetric version of the loss above. And then this is what Perl is going to give you, pretext invariant representations. You can compare it to CPC. You can compare it to Moco that we just covered. You can also do representation learning using GAN. We didn't cover this. We covered a similar paper, and then we covered deep cluster. And solving a jigsaw puzzle is here. So for the same number of parameters, Perl can do better than Moco, BGAN, and PID. We didn't cover rotation or jigsaw puzzles. Any questions? Was everything clear? Okay, awesome. So we saw another type of loss here, which is the noise contrastive estimator type of loss, which is similar, but at the same time different from the contrastive loss that we saw when we were covering Moco or CPC. Here you're using sigmoid. It's modified sigmoid. Over there, you are using softmax function. Here you're thinking from this perspective that any positive pair is data and anything else is noise. You want to increase the probability of being data and decrease the probability of being noise. With contrastive loss, you are trying to find an answer to a query that you have in a set of potential answers. You want to increase the probability of the correct answer, decrease the probability of the wrong answers. So that's how you're going to differentiate between the two in an intuitive fashion.